1.6 introduces distance or length, which is a concept that we briefly talked about in one of our first sections in Unit 1, where we were finding the length of different segments on a number line using the ruler postulate. So that ruler postulate can be used to calculate distance between 2 points on a number line. For example, if we wanted to find the length of AD. Remember, I encouraged you or suggested, hey, maybe use 0 as a halfway point and find the distance from 0 for the positive side. So from A to 0 would be 2 units. And then the distance from 0 on your negative side, so that would be 5 1/4. Add those two together to get your total distance of AD, which would be 5 plus 2 is 7 1/4. Okay. Let's have you go practice examples A through C. Well, we'll do A, B, and C together, okay? The length of BD, B to D would be a length of, and sometimes if everything is on the same side of 0, it's a positive side, you can just count, or from 5 to 1, we know that that's a length of 4. For A to C, that's using the negative and the positive side, so use 0 as a halfway point. 3.5 units. 2.5 units. Add those two together, we get 6. Okay, let's try D and E on this second number line, and then we'll let you try C and F on your own. JL, from J to L. Oh, this would be 2 units, and negative 1.5 would be positive 1.5 units from 0 for a total length of 3.5. And then for HK would be a length of, well, these are on 2 whole numbers, so let's just count the total length. From negative 4 to positive 1, that would be a length of 5 units. Okay, why don't you pause it, or the video will pause on its own. You guys are going to try examples C and F. For example 1, letter C, you should have gotten a length of 7.5 for AD. And then for JK on this segment should have been a length of 2.5. Okay. Keep in mind K is at positive 1, J is at negative 1.5. Add those two together, 1.5 and 1, you get 2.5. Okay, counting on a horizontal number line will always work until we have points that are on a coordinate plane. So when we have points that are on a coordinate plane, we need to construct a right triangle like we were doing on the warm-up in class and use the Pythagorean theorem. Okay. The Pythagorean theorem is your a squared plus b squared equals c squared. It was the formula we were using. We were finding the square areas on that warm-up in class together. Okay. We're going to stick with this Pythagorean theorem, and then we'll introduce the distance formula, which is really the same thing on the next page. But if we wanted to find the length of this segment, we can't just count. We can't just assume, oh, that's 1. That looks like it's 1. This looks like it's 2, 3. No, instead, if we want to find the exact length, we need to make a right triangle. So we're just going to drop some dotted lines down here. And now we have a horizontal and a vertical length we can count. The horizontal length is 6. Vertical length is 7. This forms a right triangle, which is when we can only use, the only time we can use Pythagorean theorem. And we would say 7 squared plus 6 squared equals c squared. Get 49 plus 36. So 85 equals c squared. Okay. And then on the warm-up in class, we simplified some radicals. Are there any perfect squares we can take out of 85? Well, 5 goes into 85 17 times. Those are two prime factors, so nothing you can take out. So we leave this as root 85. If you wanted that as an exact decimal, you could punch that into your calculator. It would be like 9.4. Might be off by a tenth, but a little bit above 9. If the directions say leave as a radical, then leave your answer as a square root of 85. That's your radical symbol. Okay, let's practice some more on the back page. Flip it over. Let's try one more together. Let's try A, then I'll let you try B, and we'll introduce the distance formula for C, D, and F. For A, let's make our right triangle. You can make it above or below that segment. Count your vertical length. Count your horizontal length. 6 squared plus 5 squared equals C squared. C will always be that horizontal length. It's the hypotenuse of your right triangle. 36 plus 25 equals C squared. The opposite of squaring is taking the square root. And let's see if there's any factors. I don't think there's any factors of 61, so we can't simplify it at all, so we're just going to leave it as root 61. Okay, why don't you guys try B on your own? Find the length of this segment by constructing a right triangle using the Pythagorean theorem. Should have had a length of 1, a length of 5. 1 squared plus 5 squared equals C squared. 26 equals C squared. Check to see if there's any factors of 26 that would work. 13 and 2. 13 and 2 are both prime factors, so we can't simplify it all. We leave it as root 26. Alrighty, let's try example D together. Let's try example D. So if you want, you can always take these points and plot them on a number line. That's okay. That's fine to do. But it might be easier to use your distance formula, which is something you saw on the previous page. So the distance formula is the difference in your x values squared plus the difference in your y values squared. That's what this y2 minus y1 and x2 minus x1. It's really the same thing you were doing when you found the horizontal length and vertical length. Horizontal up to right is x, up and down, vertical is y. So let's try the same thing here without labeling these as x2 and x1. How far is 2 from negative 1 on your number line? That would be 4 units, or sorry, 3 units. So we would put 3 squared for our x2 minus x1. How far is negative 9 from positive 4? That would be 13 units. And now we have this really the same exact equation. We're adding the two lengths, and then we are taking the square root of the sum. We're doing the same thing here. We get 9 plus 169, 178. See if there's any factors of 178 you can take out. 2 and 89. I believe 89 is a prime number, so there's nothing we can take out there, so we leave it as root 178. Okay, how about you try F, find the distance between S and T, and then simplify the radical if possible. Negative 2 is 5 units from negative 7, so 5 squared. 3 is 10 units from negative 7. That's positive 3. So we get 25 plus 100, root 125. When we factor down our 125 using our prime factor tree, 5 and 25. All right, finally a pair that we can take out. When we're simplifying radicals, we're taking out pairs. So we can take out a 5, and we're left with this 5 underneath our radical. So 5 root 5 for the length from S to T. If you would like some more practice, try C and E on your own. You're going to have some more practice on your homework tonight. The last thing I'd like to talk about would be congruent segments that we've talked about before using the ruler postulate, but congruent segments on your coordinate plane like you have right here. You have 4 segments on that coordinate plane. Congruent segments, same thing, segments that have the same length. Okay. So this problem is asking you to determine if any of the following segments have the same length. Well, let's just go through really quickly. They're on a number line, or they're on our coordinate plane. Make some right triangles and calculate some lengths. So 3, 4. Go ahead and use your Pythagorean theorem off to the side. We're going to do this for each of them. We get 3 squared plus 4 squared equals c squared. So 9 plus 16. Take the square root. Square root of 25 is 5, so we have a length of 5. Let's try the length of CD. 2 and 6. Or sorry, I believe that's 2 and 5. 2 and 5. 2 squared plus 5 squared equals c squared. So 4 and 25 gets us c. 29 is a prime number, so we can't simplify any further. We leave it as root 29. So far, we don't have congruent segments. 5 and root 29, definitely not the same number, so not the same length. 3 and 4. Oh, well, we already had a problem here that had a segment with a horizontal length and a vertical length of 3 and 4, vice versa, and that got us 5. So let's go ahead and mark those as congruent. These 2 segments are congruent, HG and FE. And let's just see if our last segment here, segment AB, has one of these 2 lengths. 2 and 5. Great. We're not going to do Pythagorean theorem again because we already had a segment that had lengths of 2 and 5 for the 2 legs of our right triangle. So we know that this is going to get us root 29. So let's mark these 2 segments as congruent. Remember, we cannot use 1 marking on each, so we need to put 2 on each of these, showing that they have the same length. And let's state this over here. AB is congruent to DC. Both have a length of root 29, and FE was congruent to GH. Both had a length of 5. Great, a lot of practice with length and distance on your coordinate plane tonight on the homework. We'll go over any questions you have in class.